All right, let's get started today. Just another announcement. So I think I kind of mentioned that I've been trying to secretly do Earth Club as outreach club. But I do want to try to put out some opportunities for y'all. Because I was in contact with the Boys and Girls Club. And I guess they have offices out in Talent and Phoenix. And so they were kind of proposing that they would love like people to come out, do some STEM demos. So if you're interested, you know, again, just let me know, because this is going to be kind of dependent on your schedule. You know, they're looking for, again, kind of after school activities. And obviously I would help you. I can't spell. Activities. Obviously, right, I can help you with all that, give you all the equipment. So we kind of have this mini repertoire of things going on. We like to bring out the ice cream for the kids, so liquid nitrogen ice cream. And then there's usually other kind of magic shows, science activities. So this would be good. Volunteer opportunities. Good for the scholarship, you know, writing essays, blah, blah, blah. They always want to hear that you're involved in the community. So just email me, and then we can figure out, you know, opportunities, what they're looking for. But yeah, I have to have volunteers before I start saying that, yes, we can go out and do a bunch of stuff, but love to do stuff. So yeah, just email me or talk to me after class. Any other questions about the course? All right, let's dive into chapter 15 then. And so now we're building upon our gas chapter, right? So we had gone through our ideal gas laws, we had our formulas, right? That was wonderful. But then kind of at the end of our gas laws chapter, we were like, well, this doesn't really work, right? That they're actually intermolecular forces, and then that dictates boiling points, right? It matters. And so now that's what we're going to be looking at as, well, what does dictate these boiling points, right? What are our intermolecular forces? So that's what this chapter is about. And then it is a little hodgepodgey because then we'll go into a tiny bit of crystal structure stuff and then talk about valence band theory. So, all right, so we start off with just our general statement. And again, this is what we're diving into. Well, what does it actually mean when we look at our chemical composition and then our structure? And of course, right, this gives us some sort of intermolecular force. So again, we'll be breaking this down. And then just note the word intermolecular. So again, kind of like your interstate highway. So that's right between states. So intermolecular forces are going to be between different molecules and atoms. And you could put somewhere, right, contrast, if I could spell, geez. So contrast to intramolecular forces, right? So those would be your covalent bonds, your ionic forces. That's different, right? Intramolecular, so within the molecule, keeping that bonded, versus these intermolecular forces. And so we want to emphasize, because again, this is something that I've seen, OCHEM students get wrong, that we're not breaking any bonds, right? When we heat stuff up, all we're doing is disrupting these intermolecular attractive forces. And so then, of course, we'll get into why things condense at certain temperatures, right? Why are certain things solids or liquids? And, again, we'll see that with our organics. Why are a lot of organic things liquids and low melting solids? And so we'll look at, again, all those. And of course, right, relative amount to the thermal energy. So obviously, as we were kind of seeing with our gas chapter, as we add more thermal energy, then our particles start getting heated up and moving around. And so again, very general trends. So when our thermal energy is high, then our matter tends to be gaseous. Again, right, how high is what we're going to be answering kind of today. And then when it's low, like again, we got into with our gases chapter, things began to condense or become a liquid or a solid. Yeah.
So in physics, we tend to look at forces like vectors. Is that, we're going to be using vectors in this at all?
No, because, yeah, as it's not the same.
So it'd be like 3 billion arrows.
Yeah, exactly.
Not in PChem, guys.
Yeah, and even then, that's just stat mex, where it ends up being, you end up rederiving your formula, basically. And again, so just basic general properties that we'll observe. So of course, if something is a gas, it tends to have a low density. Again, right, your particles are spread out far apart, so that's going to give it a low density. Shape, obviously, we remember this from our basic kind of science knowledge. So, right, indefinite shape, you remember your gas expands to fill any container. Same thing, right, with volume, so indefinite shape and volume. And then, of course, if something is a gas, and again, we'll keep diving into this, but we'll see that that means that it must have relatively weak intermolecular forces. And again, that's why we basically made the assumption that they don't exist for gases, right, for, again, our ideal gas law. But now, again, we're learning, obviously, they do, so we can make our predictions about boiling points. And then with liquids, just a reminder, so obviously the density is going to be higher, going to have an indefinite shape, right? It can take any shape of a container, but it does have a defined volume. So important to remember. I think y'all know that, right? You poured liquids before, you know you can't just squeeze a liquid into a smaller container. And then if something's a liquid, that means it's going to have moderate intermolecular forces. We're going to discuss what does that mean. And then a solid, of course, obviously is going to have a higher density and then defined shape and volume. That gives us our solid. And then if something is a solid, then that's going to indicate strong intermolecular forces. And so blah, 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 just make some comparisons. And so, right, we're just kind of seeing this laid out with our gas, liquid, and solid with, of course, water, which most people are familiar with. And it points out, obviously, the density is the largest discrepancy. Makes sense, right? Of course, as a gas, they're really spread out. Gives our molar volume. So again, right, much higher volume as a gas. Makes sense versus a liquid or a solid. And then, of course, if we remember, so the density of ice is lower than the density of liquid water, and so that is not normal for most substances. It's just that when water packs, right, it packs into this crystal lattice shape and then ends up taking up more space. Because otherwise they usually compact more solidly. All right, so liquids, again, blah, 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 just re-emphasizing that they can slide past one another so that they can take the shape of any container, but again, they're being incompressible. So again, liquids are incompressible, right? They have a defined volume. Blah, 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 so liquids flow. Just kind of trying to get through this. And so again, with gases, still kind of thinking ideal gas law and the assumptions that we made. So again, now we're saying, okay, they have complete freedom of motion. And again, we're mainly assuming that they're not sticking to each other because they're so far apart. Again, not dense. And so again, right, because there was that large amount of space between our gas particles compared to the size, that's again why we were kind of able to make those assumptions. And then obviously, like we just saw in our gas chapter, gases are compressible. And so then solids, of course, are packed close together and again incompressible. And of course, just want you to remember that, right, even though you can have a solid, there's still electron movement, right, going around. Their bonds are still wiggling and stretching and rotating, right? There's rotational freedom. So there's still molecular movement, but they just cannot slide past one another. And so, of course, that gives it its solid shape. And then we'll get into this as we go a little deeper into the chapter. And so, of course, if solids are allowed to kind of slowly crystallize, then they can make these crystalline solids, and we'll go into kind of their what's called packing structures. And then, so many of the times, we just make what's called an amorphous solid, and that can just be like powder that you isolate in lab, right? That's just an amorphous solid. Or if it just doesn't have a defined geometric pattern, such as like plastic or glass, again, those would also be considered amorphous solids. All right, so we'll start, well, actually, I don't want to start with the math. Let's skip the math for a second. And let's go with our intermolecular forces. So again, let's answer what are those intermolecular forces. And again, between molecules. So now they're attractive forces that hold matter together. And so just like before, all attractive particles are electrostatic in nature, right? So there has to be some sort of positive, some sort of negative. Opposites attract. And again, we'll kind of figure out how to determine the relative strengths. So, I don't expect anybody to just know a boiling point, but you can at least kind of arrange substances. And so you want to at least notice patterns and be able to say the stronger the attractive forces are and kind of arrange them, then you'll know who has the higher the boiling point. So again, stronger attractive forces, higher boiling point, higher melting points. So then again, we're explaining why substances are the way they are. And so again, these attractive forces vary in strength. So we'll go through kind of the main classifications of them, and we'll compare them in strength. And again, the type of attractive forces depends on the particles. And so, of course, right now we're starting to get into boiling point and vapor pressure, and we can see where this is going. And so the stronger the attractions then between atoms or molecules, the more energy it takes to separate them. So again, right, we're thinking, okay, well, that's what leads to the higher boiling point. So it's got these strong intermolecular forces. So then we have to add more energy, again, to separate the atoms or molecules. We're not breaking bonds here. And again, emphasize here again, since again, students tend to mix this up. And so again, if we boil a liquid, we're just adding enough energy to overcome our attractions between our particles. So right between our individual water molecules. So we'll get into what is involved in this, but I'm just kind of showing it. So right, we're breaking those forces between them, but we're not disrupting, right, any OH bonds or anything like that. And so again, right, we mentioned we have to have some sort of electrostatic force. So now, okay, well, why are they attracted? Well, just like before, again, we need something positive and something negative. And we'll see this, right, with a dipole. So we've seen substances that have, right, what's called a permanent dipole. So you remember that means one side of the molecule is negative, one side is positive. We can draw water, right? We've looked at water a lot. So we said, okay, it has this partial negative. These hydrogens have partial positive. All right, so there's a dipole. And we'll look at how even nonpolar molecules, though, can have an instantaneous dipole. And so that will give us intermolecular forces as well. And then, like we've seen before in some of our formulas, we have, again, our basic concept of obviously a larger charge is going to give us a stronger attraction, but then, right, that attraction decreases over the distance. All right, so this is kind of our overview, but now let's start. So now let's look at our weakest one. So this is called our dispersion forces, or sometimes you'll see them referred to as London dispersion or van der Waals forces. And so again, these are the weakest of our intermolecular forces. And so our van der Waals forces are caused by our fluctuations in our electron distribution. And let's look at the picture, and then we can go back at the text. And so here's our picture. So let's just kind of imagine our scenario. So we have our little helium atoms here. And so let's just say, right, we could take a snapshot in time. And if we look at this picture, what if it just so happens that the 2 electrons of helium, right, are hanging out on one side? So then we have this partial negative region. And then, of course, right, if all the electrons are hanging out over here instantaneously, then this is going to be partially positive. And so this can also kind of induce this instantaneous dipole. So meaning if this happens, then the neighbor could kind of be in the same position, right, with 2 electrons to one side. And now we have our intermolecular force here, our van der Waal or dispersion force. And of course, right, this could kind of chain on for a little bit. But again, this is just a snapshot, right? So instantaneous, but then these electrons are going to move around. You know, maybe they'll happen to kind of be in sync for a little bit, but probably not, right? So then they'll just keep moving around until it happens to catch another instantaneous dipole. And obviously, right, this is going to be pretty weak, which is what we expect. And so again, like we saw in their picture, again, this is instantaneous, right? Your electrons are moving, moving, moving. So it's not a permanent force, but it's just whenever you get that region that happens to have excess electron density, it gives you a partial negative next to a depleted electron density with your partial positive. That creates your dispersion forces. And so the most important part is that all molecules and atoms have dispersion forces. So even though, right, this seems very small and negligible, it does play at least a somewhat significant force. And so you do want to account for it, talk about it. And so let's look at some trends then, because like I mentioned, we want to at least kind of recognize trends. And so let's just look at size. And so as our mass increases, our electrons obviously increase. And so we mentioned that this makes our electron cloud kind of larger. And once it's larger, it can also be more polarizable. So, right, we can just so have it where it just so happens, right, more are on one side. So then we get stronger dispersion forces. And so now we can see this in our boiling point trends for our noble gases. So of course the only difference in our noble gases is just the size as we go down the periodic table. And then of course, right, note how the boiling point also increases. So helium, obviously super, super low boiling point at 4 Kelvin. And then, right, we keep increasing. So argon, krypton, xenon. So xenon, right, now has a boiling point, still obviously very, very low, of 165. But again, we're just appreciating how it's increasing with size. So that's just a size effect there. So that's one thing you want to do when trying to, again, kind of order your boiling points, is first look at the molar mass, the size. And so next thing you want to look at is the shape. And so again, we're thinking of surface area. And so let's compare these two. So now we have N-pentane versus neopentane. And of course, the first thing that you want to do is look at the molar mass for molar mass arguments. And then these are, what kind of compounds are these? What's their relationship? Hydrocarbon, but what's their other word?
Isomers.
Isomers, yeah. So isomers, so you have physical or structural isomers. And so, right, same formula, but one is the straight chain versus, right, the neopentane has a carbon in the center and then has the 4 carbons hanging off of it.
Are these considered structural isomers?
Yeah, so yeah, they're structural isomers. And so now if we compare their boiling points, so N-pentane is 36 degrees Celsius, so pretty low. But then if we compare that to neopentane, so right, it would be evaporating at room temperature, so that has a boiling point of 9. And so that is just due to a surface area argument. So again, the N-pentane and really, right, any sort of flat hydrocarbon has that large area for interaction. And so that stacks up right nicely. I don't think I did 1, 2, 3, 4. I knew I can't, too many carbons, sorry. So they can stack up obviously quite nicely, right? Get a lot of intermolecular forces versus you're seeing this, right? There's very small surface area for interaction. You know, you can try to kind of ball around, but not as favorable, right? Again, they're not kind of chaining on top. And so again, that just accounts for the difference in boiling points there. And so again, boiling point rises with increasing molar mass. So that's what's just shown here on this graph. And notice, right, these are again all the straight chains. So N just means that they're straight chain. And so we're comparing that. So we're just looking at, again, the mass effect here. So obviously, right, you add a carbon, increase the mass, and also increase the boiling point. And then it does make a note, so right, any sort of branching would obviously cause disruptions in that surface area. So branched chains have lower boiling points than straight chains. All right, our next intermolecular force then is our dipole-dipole interactions. And so again, that's where we mention that we have a molecule with a permanent dipole. And so that's hopefully why we learn to identify polar molecules, right, first quarter. We're still working on that skill, right, this quarter. Again, looking for that asymmetry. And so once we have this permanent dipole, and of course that means, right, that we have some sort of partial positive and partial negative region that can interact. And so looking at acetone drawn here, that's what's shown. So again, right, we have this permanent dipole from our CO here. Obviously, we could draw in the electrons too in that oxygen if we need to remind ourselves. And then again, oxygen, right, electronegative, and has those lone pairs. So there's our region of negative electron density, right, so our partial negative. Then that leaves each carbon somewhat electron deficient, right, in our partial positive region. And so here is our intermolecular forces, right, our dipole interaction there. And then here's also the electrostatic potential map, again, just so you can appreciate the permanent dipole, right? That's what's being emphasized here. Our blue region showing our positive lack of electron density, we should say, and then versus, right, the red for high electron density. And so again, right, our permanent dipole adds to our attractive forces. And so let's look at some of those effects. And now we're comparing formaldehyde versus ethane. So different formulas, but the first thing we want to do is still compare, right, their molar masses, make sure we're not looking at a completely molar mass argument. But they're pretty similar, right, 30, 30. So obviously not the same, but very low molecular weight, very similar. But then if we look at their difference in boiling points and melting points, right, we have negative 88 versus negative 19.5 for the boiling point. So about 60 degrees difference, right, pretty significant. And so we can see that. So then you can start to kind of identify, you know, what intermolecular forces we have. So what do we have in the ethane?
There's no permanent dipole molecule.
So no permanent dipole, so what does that leave us with then?
Lower boiling, higher boiling point.
But what was the name of the force that it has then?
The London dispersion. It doesn't.
Yeah, so right, so it only has London dispersion. So I like writing that at least, right? So we're just identifying the properties. And then of course, right, formaldehyde has London dispersion as well. But obviously, that's not the complete argument because again, right, there's a huge difference. So what does the formaldehyde have? What intermolecular force? Yeah, so then we got dipole as well, so I'll just write that. So we have London dispersion and dipole for the formaldehyde, and so that causes, right, that increase in boiling point.
Is the boiling point and melting point usually sort of, do they increase and decrease in the same direction typically?
I mean, the boiling point and the melting point are both going to increase, right, with when you have intermolecular forces, like increasing intermolecular forces, right?
Yeah, but I mean, if you have two molecules where one's boiling point is higher than the other, you then infer that the melting point is going to be higher.
Yeah, exactly. But then the difference, you know, I don't think that'll necessarily be consistent, but yeah, if something has a higher boiling point, you also expect it to have a higher melting point. And so then looking at this dipole moment, and I wanted to just remind you. And so, right, don't forget that this dipole moment, so it's something that's measured. But I always just like to remind y'all that, right, you can go to Wikipedia, because obviously, right, you can kind of look and try to judge, well, who's more polar, but sometimes it can be difficult. And so that's where the measured value comes in of the dipole moment, so where they're actually measuring, right, how polar it is, so a physical measurement. And so that just kind of helps you, again, put things into context. So we're looking at propane, just comparing what the Wikipedia page says. And so yes, right, it has a pretty low dipole moment, almost to 0. And so now we're just kind of comparing our trends here. And so of course, again, the first thing we'll note is they all have pretty similar molecular weights, right? So they're all around 44 grams per molar, so give or take. So again, we're not looking at a London dispersion argument here. So we're just looking at our difference in dipoles and how that increases, right, our boiling point. And so again, propane is almost to 0. So of course it has, right, a low boiling point, so just under 250 Kelvin. And then we can look at dimethyl ether. And again, right, all this, oops, if I could spell, geez. So dimethyl ether, again, right, the dipole moment's there, so you can always look this up later and compare if you need to. So, okay, dimethyl ether, again, right, slightly more polar. And then you can kind of compare. This is why I like Wikipedia, because it's hard to make these judgment calls sometimes, especially when you're just learning. And so, right, you're looking at the ether. Obviously, it has this oxygen in the center that makes it polar, right? So you're thinking about those lone pairs. Then if we compare that to ethylene oxide, so kind of the difference there, I could spell ethylene oxide, is it's this kind of funny cyclical compound, or in CHEM, this is called an epoxide, this little ring there. But right, it's kind of forcing it into a more bent geometry, and so that makes it just a little bit more polar, right, since this oxygen's forced more upward. And again, right, hard to see sometimes, but that's where the dipole moment, okay, it's a larger dipole moment than the ether. And again, increasing boiling point. Now let's just look up the rest. So acetaldehyde for completion's sake. And so, right, you can kind of tell that this is more polar just because we have the CO on the end here. So again, it kind of depends, right, on the location of your oxygens or electronegative groups as well. So again, just putting our dipole moment in context, okay, 2.7. And then, right, acetonitrile then, fairly polar, comparatively speaking. So we have our nitrogen on one side, right, dipole moment of almost 4 there. Double check it on Wikipedia, again, just to show that some nice sorts of chemical information. So, right, acetonitrile, we got the nitrogen on one side with that lone pair, so more polarized. Where's our, watch this one, and what will be the one that doesn't have the magnet? Oh, there it is, dipole moment. Okay, so we still have our dipole moment, and then, right, they just track like we expect, so our acetonitrile with the greatest dipole moment has our highest boiling point there. Questions on that one? Yeah.
I don't know if this is like necessarily in the scope of what we're talking about, but I've noticed that carbon has a gas phase and a liquid, solid phase and a liquid phase. I want to know if like anything in carbon explains that.
Carbon specifically?
Yeah, elemental carbon.
I mean, that's probably just more of like a tangent.
With the boiling point, or with the boiling point of water, and then like, how hot does it have to be to like disconnect like the H's and O's? And how come they can do that without electricity?
So I would have to see how much energy, I think it says somewhere in here, at least the relative strength. So yeah, this one actually gives you some at least like relative strength. So again, the hydrogen bonds, which we'll talk about right now, that they're so strong, but then there's still only 2 to 5% of the covalent bond. So yeah, you'd like, yeah, I mean, it's just like at that point, I don't know that you would do it right thermally, but then with electric, right, you're talking about different like processes that occur then, because now you're transferring, right, like electrons, so that's kind of like slightly different process, if that makes sense. All right, so then back to hydrogen bonding. And so hydrogen bonding is basically a specialized dipole interaction, and then it only happens in a very specific case. And so this is when we have a very electronegative atom, and AKA this only is for oxygen, nitrogen, and fluorine. And then of course, I should have had my periodic table pulled up. Otherwise, right, you can turn around and note the location of those will obviously They're in the upper right corner, so that's why, again, it's just those three, right? Your most electronegative elements. So again, fluorine, oxygen, nitrogen. If you need to star them, highlight them, whatever. That's the only time that you'll get hydrogen bonding. And so let's look at why. And so again, hydrogen obviously just has our 1s electron. And so then once that electron is pulled away, then the nucleus becomes what's called de-shielded. So just meaning essentially you have almost, right, like a naked proton there just hanging out. And so then this exposed proton is obviously a very strong center of positive charge. And so it attracts, right, the electron clouds from any neighboring molecules.
Are those the only three elements that hydrogen bonds to?
Yep.
What about carbon?
Nope. So only those. And so, right, we could be looking at HF here. So again, right, extremely polar. And we could probably get into, right, why it's a liquid. I'm sure it's high boiling. And again, right, we're showing this electrostatic potential map that also gives us this idea of how polar it is, right? Very blue for our poor little naked hydrogen versus, right, very red for that electronegative. In this case, if we're imagining fluorine for HF. And so again, right, you're appreciating how large that cloud is since it's pulling all that electron density towards it. And then obviously, again, with this being so polarized, so now you can have your hydrogen bonding interactions there. And so again, right, highlight this, star this, hydrogen bonding is the strongest intermolecular attractive force. So, right, it's stronger than our dipole-dipole, and then obviously stronger than our dispersion forces. And so now we're kind of seeing the beauty of water again. And so, right, of course, water is kind of an anomaly, perhaps, since it's so small, right, 18 grams per mole. But obviously, right, a boiling point of 100 degrees Celsius from those hydrogen bonds, right, it has two hydrogen bonds. So that's something else to think about, or two spots to hydrogen bond, right, so off of this and there. And so again, right back to your question, that yes, right, we're putting in so much energy, but we're not breaking any chemical bonds. We're still nowhere near breaking chemical bonds. And so now comparing boiling points once again. So looking at ethanol versus dimethyl ether. And so, right, maybe you could try to make a dispersion argument. You could look up, right, their dipole moments if that helps you. So diethyl ether, oh, dimethyl, my bad. So we can look at dimethyl versus ethanol. And so we can at least see, right, so ethanol has 1.69 for its dipole moment versus dimethyl ether. So 1.30, right? So not that different. So obviously, right, ethanol is a little more polar. But then, of course, how many hydrogen bonds does ethanol have? How many potential places? So one, right, it has one OH group. So, oh, there we go, 1, 2 carbons. and then attached to OH, so right, our ethanol. So there's our, right, H there, appropriate for hydrogen bonding with another ethanol, versus our dimethyl ether, right, we can draw it out. And this oxygen is not attached to any hydrogens, so we have no hydrogen bonds. So no H bonding, right? We can still, of course, write that we have dipole-dipole. And London dispersion. Don't want to forget about London dispersion. But then again, right, huge difference, really. So negative 22 versus 78. And again, most of that is from the hydrogen bonding. So if it had just been, right, a dipole argument, this would only be probably a little bit higher, right, since they were pretty close in a dipole moment. So I think it was like 1.6 roughly, versus 1.3 or something. So, right, very small difference. So again, it's from that hydrogen bonding. And then,
Does the dimethyl ether with its dipole-dipole attraction form liquid crystals?
I don't know what you mean by liquid crystals.
Like crystals that are formed with electromagnetic properties. Because water has the same sort of thing, so it's akin to that.
Yeah, I mean, I don't really know, yeah, that's kind of tangential. All right, so then our last kind of attractive force, which this kind of gets mixed in, I think, at least in your book, kind of where we should put this. Because this is kind of stronger than our hydrogen bonding. And so this is talking about kind of, right, like why ions dissolve again. And so now it's just mentioning, right, this ion dipole attraction. Some more answering again, why things dissolve, or really, right, ionic compounds. And so now we're kind of seeing, okay, well, that's why ionic compounds, right, readily dissolve. And so again, right, this is just emphasizing, let's say we have sodium chloride, and all it's saying is, of course, right, your chlorine then, obviously it's negatively charged, and so now all your waters are going to point the hydrogen towards the chlorine, so it helps solubilize, right, and nucleate it there. And then, of course, right, opposite for the sodium, all the oxygen ends are headed towards there. And so again, right, this is obviously a very strong attractive force, and again, leading to solubility, so we won't go into solubility right now. And so this is what I mean with these intermolecular forces. Again, we usually just don't talk about ion dipole in terms of intermolecular force, but it's kind of thrown in there with your book, yeah.
You see how like the water is lined up and like the hydrogen, or the hydrogen bond, right? How they're attracted. Does it sit like a certain way in gravity, or is it like random?
So it's going to be like random, right? Because so you have to think about, and this goes back to why the ice has a lower density. So let's just look up structure. So, right, you have to think about, okay, even though it's experiencing these forces, right, it's still a liquid. So it's still, right, moving around. So it's going to have hydrogen bonding. But then, let's see if we can get a picture.
So like the forces of it like moving around and stuff are greater than the
Well, there's just, yeah, there's going to be enough motion, right? Because that's the thing. If it's in the liquid state, you're still saying that you have enough motion, right, and enough energy to slide past. But then once you talk about, like, especially water again crystallizing, right, yeah, it's going to crystallize in this way, right, as shown here in this ice crystal lattice because of the hydrogen bonding, right? So now you can see that, okay, well, that's why this is positioned that way, right? And it's in this repeating structure where it's all this hydrogen bonding. So yeah, once you get it in the solid state, it is kind of more frozen like that. And again, right, that's what makes it less dense than water. Very unusual, right? So usually you don't get this kind of organized structure like that. But yeah, otherwise, right, they're still moving around, so.
You feel like a magnet will like, kind of like follow the,
Yeah, well, you can make like water bend, right? Like you've seen that.
yeah.
But I don't know like what sort of things that like people have done with like magnets and water necessarily.
That static electricity is a different kind of magnetism.
Yeah. Well, I mean, it's still just like polarized forces, right? So you're showing that water is polar once it reacts, but
Alright.
yeah. And there's like other weird like fringe stuff with water that people have tried to do. Like, gosh, I can't even remember because somebody did like a research paper on it like a few years ago, just like these weird phases. But yeah, I don't know enough about that.
Is there anything you can dissolve in water that will cause it to freeze in such a way that it'll have a higher density than it would if it was free of materials inside of it?
You gotta stop asking like random trivia questions, you know? Like I'm not trying to knock you down, but it's like you ask for like a really random scenario. That like I don't know. It's just like it's not questions that are really relevant or helpful. I'm sorry, I'm not trying to be mean. It's just I don't even know what you're asking. Okay. So then, again, right, comparing these boiling point trends. So let's look at, right, obviously some anomalies. And so now we have, right, molar mass argument, so looking at group 4. So methane versus silane versus our germanium hydride. And again, right, molar mass argument. And then obviously, what's our anomaly? So water. And again, right, this is just emphasizing, right, our hydrogen bonding. So that's all we're getting from that trend. And right, also kind of saying, well, yes, sulfur is pretty polar, right? Like I would consider this a pretty polar element, but still not polar enough to induce hydrogen bonding. So that's what we're appreciating here as well, right? So these have lone pairs with our group 6, but again, only water has that hydrogen bonding. And then again, this other chart, I believe this was from your book. And again, right, just noting our 3 exceptions from our hydrogen bonding. And then just comparing all our different rows. So obviously our noble gases, then the group 4, and then right group 5 up here. So again, right, with our anomaly of nitrogen. And then halogen compounds, group 6. So again, just noting the anomalies. Okay. That's a good spot for a break. So let's take a 10-minute break, and then we'll dive into the math of it.
Dissolving of salt and like the ion.
Sorry?
The dissolving of salt and ion particle interactions, they don't actually like pull the atoms of salt apart.
Well-
It's not like poisonous to us.
Well, I mean, it dissolves it, right? So it does pull, like, the ions apart, right? But it doesn't make it into sodium metal, right? It's just sodium ions floating around the solution. Like, that's how it dissolves.
I thought they were like sodium and
Yeah,
Poisonous.
they're not poisonous.
Oh, I thought they were.
Well, if you have sodium, right, sodium metal, but once it's sodium as in, well, in a, like in a compound, like an ionic compound. So once sodium has given up its electron, then it's not
Oh, okay.
toxic, yeah.
Speaking of sodium, I decided that for my research this year, I'm gonna do some research on liquid metal fast reactors. They're starting to experiment with using a sodium alloy as the liquid coolant for reactor pools.
Oh, I think I've heard of that, yeah.
I actually, I'm having I know that there's a lot of like movement around research in it, but I'm having a hard time finding like specifically journal articles.
Yeah, I was gonna say, maybe you have to even look at patent
Yeah,
things.
and we're allowed to do that.
Yeah,
I was looking at Google Scholar and I found some.
So with like heat and electricity, is like heat more like the speed and like if you like heat something up, it just increases speed and then like electricity, electrons.
yeah, exactly. Because yeah, heat, you're just talking about like, right, its relationship to kinetic energy and speed. But then with electron transfer, you can talk about actually shuttling stuff, and then that gets into like one electron versus two electron versus multi-electron processes, right? So sometimes you can just, even if you're feeding it electrons, right, you're not feeding it the correct amount. Yeah, and so that goes into like complicated.
I looked over and you were
Making like a, sugar, like a plant, right? Like a plant converts CO2 to sugar. But how come you can't just
like 3 times.
juice it up? Yeah, it's not that simple. Yeah, except it's like, I can't remember now if it's a 6 or 8 electron process, but right, it's a multi-step chain
So a lot of that
reaction when the plant does it, so that's why, even though it's multi-electron, it does.
Swear,
That's
I'm
where
reading
chemists
my
have
high school
trouble.
teacher
Because
explain.
no simple compounds only either do 1 electron or 2 electrons.
Well, one.
Yeah, with the gas density and stuff,
I'm
when
gonna,
they
when I have my notebook from high school, I'm gonna just like start writing
Right,
down.
sorry.
I'll email it to
when you get like 3 moles of H and then a mole of N, and then they combine to make like this 22.4 volumes. It's like, I think that's why I think kinetic engineering is pretty cool, because you make like a lot of like pressure systems and stuff. Like,
Oh, yeah.
I think it'd be able to make that, just like he did like something, and it would like work on like pressure and things.
Yeah. And there's a lot of different limitations, yeah, so those kind of sound like Haber-Bosch process, right? Or,
I looked something like this article. This is from the World Nuclear Association. Or should I use its references?
it's probably better to use those references, but, yeah.
See that hurt. I was like,
And just like snort of my and just
no, don't drink it. Snort.
yeah, I gotta get it right in my
In the center. No, sorry, right there.
and then just
Does it work? Does it work? Like, if maybe we try?
yeah. And like I did really late. It's have to be more better than scheduled.
There's a lot of like,
It's kind of bad.
what I'm finding a lot
So
of
it's
is
not
like
in our control.
laboratories is
Oh.
setting
Maybe
their
a little bit.
positions on the
Don't get no big. When I
and
have time.
like, and then,
No.
So I'll go on there just to like, oh, click boundaries.
a lot
And
of
it's like
demonstrations
10 hours later.
Mm-hmm.
of
I dedicated the day to be homeless. And I did that day.
I've actually left up on me too. Like, I'll keep myself at home. I'm like, oh, very nice.
I wonder if
well,
I'm
time to go
interested
back.
in the outreach.
Oh, yeah.
It's like, it's not even really season, like, it'd be fun to do.
What's your schedule like? Are
And I
you
start
free
And then,
after school? Like, any day, Wednesday?
yeah, pretty much. I usually.
I guess after school,
Yeah.
like,
It's not the first
what
one I've
time do
gotten
you
it.
get out?
Yeah.
3,
I've
4,
got-
yeah.
I well,
I've
one class
got-
each day.
I've gotten so many, I've
So I'm
gotten,
usually.
so the
except
biggest
for
ones I've
Tuesday
gotten
for
is
the lab,
like
free,
Peter Parker and I
get out
went
at
to
1.
Walmart.
Sweet.
And I was like,
Yeah, sometimes I drive my sibling home and they get picked up at
I never
3, but
thought
they can
about
also take the bus, so
it's
that's
ridiculous.
fine.
how many-
Yeah.
And I'm out at noon on Fridays. So it's
There was one
class.
girl at my
Okay,
house.
so you're pretty flexible.
Every
Yeah,
time
pretty
she goes,
yeah.
she goes, hey, it's Peter Parker.
All right, I'll put you down.
I wish.
I also
I was like, I
asked
wish.
for
I could.
a letter of recommendation
Oh
for
my
our
God.
AU program.
Oh, yeah.
Yeah,
That'd be
I realized the
I wouldn't want
deadline's on
people
the first, I'm like, oh no.
No,
It was
that's
quickly,
Well, because, like,
sorry.
Email me, like, ASAP, like, yeah, kind of, because, you know, for those RU things, they also
Yeah.
want to know, like, what have you done in the community, so just like, give me some
Yeah.
background on, like, whatever your volunteer,
Now
yes
doing
is, you know, like,
Okay.
any little thing
Honestly, I
to
think
stretch.
Mhm.
I mean,
Yeah, and then
I
if you
can't-
send me
I
like your
can't be-
CV,
Well,
just like, have a
People
general
need
background.
specific
And then anything else you think is relevant that I can talk about,
Dude, it's like,
Yeah.
I've gotten that
But then-
so much.
Yeah,
Whenever
yeah,
I
yeah.
wear striped
Yeah.
shirts,
Thank you.
I was thinking,
Will do.
Yeah.
you know, and after you said that, I was walking to RTC, and I was like, I was running from my mom, and I was like, striped, striped, striped.
One of the things that I want to do for the,
It should be on Blackboard still, although just new Ultra,
jeans and still look nice.
I don't know if they're allowing late assignments.
Literally-
Have the drip. Oh, it's allowed late assignments.
Thank you. No, my dad took me to my house, and he was like, I'm gonna buy you this. I was like, and he was like, there were so many colors. I was like, I was gonna go for either like a light kind of like mint green, a cherry red, or
Oh, it's under week 2. And hopefully it'll still
I
let
want
you
cherry red
submit.
really bad. I was like, this is what was that?
Oh, the paper
Because
topic
he was like,
selection,
you're going
you
to
know,
college.
do
He's like,
that.
I'll be He spoiled me.
It's like, enjoy while you can.
Oh, I know.
Enjoy it all. And get those shoes.
I'm going to find my minutes. Absolutely not.
Without something like this.
That is
I've had
interesting.
so many instances, not like that, but like instances where like I'm embarrassing. I feel the pain.
Yeah, I mean, you can
feel
cite
it.
that. I still try to look at like whatever the primary things, but yeah.
Yeah, they're really hard to find.
Yeah, that's what those.
I can switch to a different thing.
No, I think it'll be okay. We'll just have to figure around.
I could also, I can call the OSU's Tennessee
The first.
lab,
So I get
because I know that they're working on it and see if they
You only needed
can
those for-
recommend or send me any papers.
And now we had not typed on.
All right, do we make it back from break? All right, so now for everyone's favorite part, math, quantifying. And so especially y'all being 200 level students, right, we're gonna obviously look at an example of water, but then you may be expected on an exam, right, to do any substance provided obviously relevant thermodynamic values. And so let's kind of break this down of what we're trying to look at. And so basically, right, this is just a heating curve, but we need a breakdown of what exactly is a heating curve. And so let's look at a few things just before we look at kind of the math. And so, right, our heating curve of any substance should ideally show us, right, all 3 states of matter. And then we can also point out, right, relevant points of interest here. So what's happening at these flat places? One.
Energy is being put into breaking bonds instead of heating the substance.
So breaking bonds or intermolecular forces, what's another way to say that? What's going on simply? More simply?
What?
Like, what's another way to phrase what you said? You said everything correctly, but
In heat of fusion and heat of vaporization.
I was just going for more general, like, state change. Sorry. You guys are going too specific. But yeah, just right, changing matter. So right, like Vaughn said, breaking our intermolecular forces. So right, the energy is going into breaking the intermolecular forces to do our state change.
Physics changed.
And so then we can, again, we'll look at kind of what those terms mean again. We'll dive in. And then, of course, we're noticing our states of matter. So down here, it's probably a solid, and it is labeled there for us. But if it wasn't, right, kind of piece it through. Then we have a state change. So then that's liquid over here. Then another, right, state change. And then, right, our gas phase. So, okay, kind of breaking it down. And so, obviously, this is water. But if you didn't know your melting point and boiling point, you could go over to your substance, whatever substance this is. And, okay, this is my melting point. So, obviously, 0 for water. And then, obviously, right, it corresponds to 100. Again, this is water. You could look at any substance. All right, so then y'all were throwing out some terms, which was good. And so then we have what's defined as the heat of fusion. And so again, right, you're 200 level students, and now you have to be prepared for any way that the heat of fusion could be given in, could be given in joules or electron volts, whatever you're looking at, reference material. And so, of course, this is for melting. So fusion, so melting or freezing. And then, right, obviously melting is endothermic, meaning it requires energy. So if we're going in the forward directions from left to right, you're adding energy. Of course, you can go reverse. Then you would just have to lose the same amount of energy. And so it mentions that here. It uses the term crystallization, right, but that's just freezing. And so our change in energy of crystallization is opposite of that of fusion. And so then our next term, our vaporization. So then that's just, right, liquid to gas or evaporation. Going the other way, right, condensation. And so again, obviously we're going in the forward direction. So our vaporization is positive. Again, right, obviously if you're going in the reverse direction, you have to lose that appropriate amount of heat. And then just some general trends. Well, obviously, right, the heat of vaporization should be much larger than the heat of fusion. Well, that makes sense, right? The gas has more energy, they're further apart. So obviously, right, we expect that to have more energy. And then if you're ever given a sublimation problem, but you're not specifically given the heat of sublimation, then you can calculate that just by adding your heat of fusion plus your heat of vaporization. Since again, right, sublimation is just going from solid to gas, or obviously, right, vice versa, if you were doing deposition. And so again, on the exam, right, I can give you any substance and provide you with its relevant heat of fusion, heat of vaporization, etc. And so again, you can see how it might be given. So it might be given in this kilojoules per mole. And so, right, again, this is where it's very unit dependent. So you just have to really pay attention to what units. Obviously, if it's in kilojoules per mole, right, you'll have to convert your substance amount to mole. And so then we also need to quantify its heat capacity. So basically, right, how much heat can a substance absorb? And this is proportional to the mass. And then, right, obviously the specific heat of the material. We should also add in here the state of matter, as that is also important. And so, right, you can obviously know your quantity heat absorbed if you know the following. And you did this with your calorimeter kind of last quarter, if you can remember back. And again, you kind of more did it blindly. That was one of those instances, right, where I just kind of gave you the formula and you frantically kind of punched everything in. But if you kind of go back and think about what happened, you can kind of, right, repiece together this formula and kind of what we did, right? You did some stuff with your change in temperature, right? Quantifying how much heat you were giving off in the system, right? Remember you did those magnesium reactions, like dissolving magnesium in HCl, measuring the temperature change, and then you were able to get joules out. And so this should be a pretty good formula. Again, like everything in this chapter, pay attention to the units, but typically your specific heat is typically given in joules per gram degrees Celsius, and that obviously means your temperature change. Obviously, right, degrees Celsius and Kelvin increase the same, right? So a 10-degree difference in Celsius is a 10 degrees difference in Kelvin. That's all I'm saying there. So we just need our change in temperature. And then just make sure that the specific heat is indeed mass dependent, right? And you're not looking at it given in moles. That would be the only weird thing. It could happen, though. All right, so then the rest of this just walks us through the math specifically for water. So we'll go through it. But like I said, on an exam, you could be given any substance. And so the goal of this problem and how it would be phrased is like, how much energy does it take to take 1 mole of ice at -25 degrees Celsius all the way, well, we want to take it ultimately all the way up to 125. So that would be the overall problem, which perhaps I should write up here. So write goal, and this would be again your exam. So heat 1 mole of H2O from -25 degrees Celsius to 125 degrees Celsius. And then, right, again, the problem would say calculate the energy or something like that. And I would not tell you boiling points or melting points, right? I would just, again, give you all the relevant thermodynamic data on the side. And so then let's kind of go through this process, what you would do. And so, right, the first curve here is, right, to just heat from our cold to the state change, essentially, right? To the first state change. I'm just trying to make it as general as possible. And of course, for water, that means we're going to go to the melting point. And so that's the math that's shown here. Again, right, just putting everything in the appropriate units to go along with the formula. And so obviously we had to convert moles to grams. And this is where the state of matter matters. So if you look at the heat capacity for ice, you'll notice it's a little bit lower than for water. So the ice heat capacity is 2.09 joules per gram degree Celsius. So that goes in here. Again, right, this would be given to you. You would have to calculate that, right, figuring out what's your starting point, where's your first state change. And again, just watch units. So I'll just punch it in so we're on the same page here. So 18 times our specific heat. Again, you can see, right, units cancel, times 25. And then, again, this was in joules. And so I would put it in kilojoules for easier addition later. And so, okay, so now we're at our state change. So now we're here. And so again, it breaks it down into our second segment. So, right, this is now our state change. So again, solid to liquid. And again, right now we're just getting the relevant pieces, so you'd be provided with the heat of fusion. And then again, right, use the units to help you. So, okay, if your heat of fusion is given in kilojoules per mole, then, right, we just need our molar amount. That kind of helps us too. Oh, right, we're just doing a state change. I don't need any temperature difference here. And so then, right, we just have 6.02 kilojoules to perform that state change of 1 mole of ice. So, right, now that takes us to this point on the curve. So we're ready to add heat. And so now that's segment 3, right? We're going to heat our substance. So again, right, I'm thinking I need heat capacity. And so that's exactly what we need to do, right? So we're given heat capacity. So again, this would be provided on an exam for any substance. Obviously, again, water is amazing. It has a very high specific heat, 4.18 joules per gram degree Celsius. Right, we could go into, that's why we've had such wonderful mild winter this year, relatively speaking. So wonderful Pacific Ocean keeping us relatively stable temperature-wise. And so again, right, just watch those units. Obviously, it's in grams, so this has to go to grams. And so that's all that's done here. And again, we took it all the way up to the boiling point. So we're ready to do the next state change. I'll kind of put that up, right? Heat up to state change. So again, right, obviously that gives us 100. I'll punch it in. Let me know if you have questions. And so then we get 7,500 joules roughly. So again, 7.52 kilojoules. So now we're, again, appreciate where we're at, right? We're ready for another state change. And so now that's what we're doing up here. So state change. Now we're going liquid to gas. So we need our heat of vaporization, right, for our state change. Again, this would be provided. We're given these units, kilojoules per mole. Use those units to help you. So now we can just multiply by 1 mole. So that gives us, right, our 40.7 kilojoules. It's not too bad. And, I mean, I like this chart. Obviously, you're not going to have this chart drawn out when you're doing it. But I just want you to, again, appreciate the relative amount of energy that took for that state change. Again, comparing, right, your melting state change now versus our boiling state change. So a large amount of energy. So now we're here. We've completed our state change. And so now we can do the last bit that it asked for. So heating our steam from 100 to 125. So again, this is where we need our heat capacity for our specific substance right at the correct state of matter, so at the steam state of matter. again, the heat capacity of water drops back down to 2.01 joules per gram degree Celsius. Again, right, use your units. So obviously we need our moles back in grams. So 18 grams times our specific heat times our change in temperature, so obviously 25 degrees. And then I'll multiply it just so we're on the same page. Times 25. And so that gives us, again, 0.904 kilojoules. And then we just want to add up the total energy at the end. So what was, right, the total energy for this process. And so now we can add it up in kilojoules, 0.904 plus 40.7 plus 7.52 plus 6.02 and plus 0.941. And so then, right, we have our total energy of that process of 56.1 kilojoules roughly, again, to take 1 mole of ice from negative 25 degrees Celsius to 125 degrees Celsius. So again, any questions on that? I know I went kind of fast, but hopefully the dimensional analysis should be guiding you, and you should feel okay about this. Yeah.
On the maps, you were doing like 18 per gram, so it's like one.
Yeah, so if we had 1 mole, right, then we just converted it to grams. If,
Yeah, would that be per mole that it's converted or?
yeah, so then I just multiplied it by the molecular weight.
Okay.
So if it was, 2 moles, then it'd be 36 or whatever.
Yeah.
And then obviously, right, different substance, different molecular weight. All right, let's continue with other properties. Again, kind of dense chapter. And so now we're just kind of putting the little pieces together of surface tension and other properties. And so surface tension is just defined from our tendency of liquids to minimize their surface area. And so we see that our liquids are forming a spherical. So, right, liquid forms drops, and we'll see that. And so our surface tension is, of course, related to our intermolecular forces. And so technically it's defined as the energy required to increase the surface area a given amount. So this is now just comparing two substances. And so let's look at what we want to take away from this. So we're looking at water versus benzene. So remember, benzene is this substance, C6H6 here. So this guy. And remember, right, these are carbons at every point. You have one hydrogen. Yeah.
Is the H not connected, when you said H is not, is that like, H is not connect, H is connected to F, O, and N, is that just for like dipole moments or?
Yeah, and here, right, we don't have any hydrogens connected to H or N, right? So that's always relevant. Here we do, right, with H2O. And so, okay, this one has hydrogen bonding, right? Our water does. This one does not, no H bonding.
So when hydrogen is connected to F, O, or N, that's like hydrogen bonding?
Yeah, yeah, so anytime it's there, you always have the hydrogen bond. So yeah, specific case. But yeah, you want to look for it. And so, right, we kind of identified then our intermolecular forces. So again, if water has our hydrogen bonding, right, we know it has stronger intermolecular forces compared to benzene, which is relatively nonpolar, but we won't get into this pi delocalized system, which kind of helps it become polar-ish. But anyway, so we're comparing our surface tension. And so again, right, water has a higher surface tension because, again, stronger bonds, so that makes sense. We want to see that. And actually, I'll go to demo cam. Hang on, give me a second. Only works for the streaming people. Can I do this? Oh, come on. Okay, that kind of works. Oh, gosh. Sorry. Weird camera work. All right, so let's look at our surface tension. I'm still not happy with this. I'll have to fix that later. All right, so let's look at some examples. There we go. That might work better. And so I want to just point out our little phenomenon here. And so if you've never done this in school, you might want to play around with this. So we have 2 pennies on screen. And so now what we want to do, so I brought cyclohexane and water. And so the idea, again with surface tension, is if we have stronger intermolecular forces, we should be able to get kind of more drops on. And so this is something you might have done like in school, maybe with just water, where it's like, how many drops of water can you fit on a penny? And right, that's always really exciting. And so I'm not going to count. Do we see this on camera? So right.
You might want to pull down the blinds so that you have better lighting.
Pull down the blinds. I don't know how to pull down the blinds any further.
Same difference. Only.
I don't think that makes any.
Doesn't.
No, it makes like 0. Try to get a little lower, because I don't know if you can see. I'm just trying to show off how big that bubble is. I don't know if that's really.
You need a source of light to diffract off the water.
Yeah, well, I need a lot of help, so.
Do you want me to just flashlight it for you?
If that works, so. I'm going to try to put cyclohexane on. Nothing is helping.
Nothing is helping.
So let's see. So cyclohexane. I already spilled some over. And so again, I might try to take the camera off. Oh, I already messed up. So the cyclohexane, as you can tell by my little bubble that's spilling, I don't know if I could. Sorry. That's why I need a producer. Oh, come on, come off this stupid thing. Okay, let's see if that works. Yeah, so kind of tell more now that I'm hand holding it. And so again, right, I kind of broke my cyclohexane already.
Oh, that's me. Ew.
I'll try to, there we go. And so again, right, you can see the water at least from there. Obviously, right, has that huge bubble, at least now it looks big, from this angle versus the cyclohexane, right, that's over here, where I could not get as many drops on there.
Marissa, what do you like?
I was just, oh. All right, well, that's one way to smash the experiment. So now we'll go back, sorry. Copy of a copy there. All right, let me, before I spill everything. And so, right, you can play with this later after class or in lab if you want to play with it some more. But hopefully the side angle kind of gave you a sense. Sorry, I lost my cap now for cyclohexane. That's good. Safety first, guys. All right, well now we'll just breathe in some cyclohexane. It's not too bad. Find that cap eventually. And so again, right, just like we saw with the little demo, so the higher our intermolecular forces, the higher the surface tension. And so again, right, that's why you can get a nice big bubble for water versus any other sort of hydrocarbon. And then it does, right, mention a few things. So of course, if you were to raise the temperature, that would reduce the surface tension. And so, right, obviously, you're just increasing the kinetic energy. So if you're increasing, right, the kinetic energy, you disrupt those intermolecular forces. So that makes sense. And so surface tension, we have, again, now we can use our properties of surface tension to kind of float paper clips or other things. I don't know. Sometimes I show this video of a lizard running across the water. I don't know if people want to watch that.
Always.
Always. See if I can find our lizard here.
At US Cellular, you don't have to choose between a great deal on the phone you want and the...
Not signed into my premium YouTube on this one. Go away. No. Okay.
Lizards are looking for food. Basilisks have been nicknamed the Jesus Christ lizard. Why? This adult male, probably the father of the young lizards, can't tell us. Nor can this female, exclusive property of the territorial male. It has nothing to do with the feeding habits of the basilisk, which consists primarily of insects and berries. This predatory reptile will help reveal the secret as it stalks the young basilisk. The basilisk is called the Jesus Christ lizard because it can walk, well, really run on water.
All right, I just love that video of the lizard running. And so again, right, obviously the video is getting there. And so, right, he's running and moving really fast, taking advantage of, again, surface tension. And so, again, the thing to take away is obviously, right, the lizard is more dense than water. However, he can, you know, take advantage of surface tension temporarily to run across. Or like I think your book mentions, that's why you can, again, float that paper clip since it has, right, all the little, what do you call it? It has like a space here where obviously, right, you can have surface tension for your paper clip versus, right, you straighten the paper clip out, it'll sink. So viscosity is also related. And so viscosity is just defined as the resistance of a liquid to flow. And so just good reference. So it's given in these weird units of these poise. and centipoises. So water is 1 centipoise at room temperature. That being said, again, we don't really talk about viscosities, just rather relative viscosities. And so as you might imagine, so larger intermolecular attractions equals larger viscosity. Again, kind of just keeping it to our simple substances, right, our hydrocarbons. So again, we can see increasing viscosity.
It's kind of why they say that glass is actually technically a very, very viscous liquid, because it's just a bunch of silica and molecules changing together, right?
Yeah. Did you hear what Mom was saying? So like glass is a slow moving liquid actually. So like, especially in the older, like an older home, apparently the windows will be more thicker at the bottom. So that's cool.
What are the SI units of poises?
So poises is 1 gram per centimeter. And then second, yeah. I believe it's in the numerator on top since it's multiplied by second. And so again, higher intermolecular forces, a higher viscosity, and the more spherical a molecule is, the lower viscosity. So, right, obviously if it's spherical, we already mentioned how it has those less surface interactions, so that can lower your intermolecular forces. And just like you imagine with our surface tension, so right, we raise the temperature and that reduces its viscosity. And probably think about that with like honey or something that has a much more slower or higher viscosity. So you might want honey to flow faster. Versus you probably, at least for our practical applications, don't care about the difference in viscosity.
Is viscosity like how slow it is, or
How
how
thick
fast?
it is.
Yeah, it's like kind of how thick it is. Yeah, so like how it flows, but then something that has a high viscosity doesn't flow.
A good example I like to think of is why they recommend you heat stainless steel pans dry without oil in them, is that the oil will disperse in a hot pan better because the viscosity will immediately drop and coat the entire surface.
Yeah, so that's a good example with the oil, and you can see that pretty readily too with the oil spreading, so that's good. And then, so other pieces of the puzzle are capillary action. And so, right, capillary action is, of course, just defined as the ability of a liquid to flow up a thin tube against the influence of gravity. And so, obviously, right, the liquid rises until gravity counteracts the capillary action. The narrower the tube, the higher the liquid. And so, right, you have kind of two forces working together. So you have your cohesive forces for your liquid, right, that are holding your liquid together, versus your adhesive forces, so how much your liquid is attracted to the tube's surface. And then I also like to take this time to point out that, so one of Einstein's first papers actually was on surface tension and capillary action. So, I don't know. I always feel like if you ever feel bad about yourself, like just feel like Einstein was also making normal papers and could write about capillary action. And it's also kind of funny because I don't even know if it's really that relevant since he tried to turn surface tension into this two-body problem. So this paper, and I could share it, but basically they just kind of say that he had some difficulty getting published, and blah, blah, blah. So don't give up. So yeah, he said, I think this was his like second attempt to like publish or something. Yeah. So he wrote about difficulties in publishing. So you can see that hasn't changed in science. So obviously, right, he eventually did other things, but, and I believe, where's the link? Oh, sorry, I didn't click on it. And so there's a link. So obviously, right, this is historical stuff now. So now this is public. Again, I can post a link if I remember. Not that relevant, but you can just appreciate the paper that Einstein was trying to write. So again, he's just going through this kind of two-body derivation. Blah, blah, blah. And basically, he was just finding these deviations and calculating surface tension or something. But you can look at it. So interesting historical context. And so then we have our meniscus. So this is just our curving of our liquid right in our tube. So either due to our competition between our adhesive and cohesive. And so now we understand why water is concave. And so water is concave in our glass tube since water's adhesion to the glass is stronger than the cohesion to itself. So that's why it's kind of rides up a little. But then of course, right, we measured the bottom of the meniscus. And then for mercury, it's opposite, so it's actually convex. If you were to see a mercury manometer, which hopefully you will at some point. Mercury has a really bad rap. And so again, now mercury is attracted to itself stronger than the glass. So again, it's convex. And measure from our top of our meniscus there. And so, of course, highly, highly related to this is our vapor pressure, which kind of mentioned a little bit with the water, right? So we talked about the normal boiling point of water. And so we have, again, our pressure exerted by the vapor when it's in dynamic equilibrium. So again, right, like what is our water exerting at just room temperature? And so, of course, the weaker the attractive forces, aka, right, the lower our boiling point, the more molecules will be in the vapor. And again, that makes sense. So, again, weaker the attractive forces, the higher the vapor pressure. And I always like to think about, and I don't know if y'all are of drinking age, but I'm not really a drinker, but you know, you like open up the Franzia bottle or your alcohol and you're just hit with that smell. And that's really because of the higher vapor pressure, right? So then you're just getting hit in the face with your ethanol. Or if you ever open up an ether container on a hot day, it'll like, yeah, it spews at you a little. So you got to be careful, stand back. And again, right, obviously, higher the vapor pressure, the more volatile, which I think we're seeing. And then this is a good chart. So again, just showing our vapor pressure curves. And so we kind of saw water, again, when we were trying to figure out the vapor pressure of water at room temperature. And then note, right, when it reaches 760, obviously that's considered the normal boiling point, since that's 1 atm. And then obviously, right, when any substance crosses our normal boiling point, that's considered the boiling point. Questions about this one? All right, so then we'll see how far we get with the phase diagrams. Oops. So now phase diagrams are, again, just another reference material. So we're looking at it for water, but you can have a phase diagram for any substance. And so what we want to take away is just kind of how to read it, our different regions, and then what they represent. And so let's look at it. And so then you might want to highlight on notes or just kind of draw a general outline. So right, you'll have your solid on the left side over here. And so some, again, points to note. So it tells you, right, you have your fusion curve. So that's telling you, right, your state change. So write your energy going from solid to liquid. And then write your sublimation curve. So obviously, right, this is solid to gas, so just comparing. So down here is all the conditions at which water is a gaseous state. So again, right, we have pressure and temperature on these charts for this phase diagram. So let's just look at our curves here. So gas, and then liquid is over here. So again, I label this, right, solid, liquid's going to be up. And so then, right, this line is a vaporization curve, again, state change from liquid to gas. Then we have the triple point. So that's the area where all three states of matter can occur. So there's triple point, which all three states exist simultaneously. And then our critical point is kind of our furthest point on our vapor pressure curve, where we have this kind of supercritical fluid. I don't know if I have a good, and that one's kind of a hard, I don't know if I have a good graphic ready. Let me look it up. Well, oh yeah, here's what I'm thinking of. And so this little graphic, I think, kind of helps you understand what exactly this supercritical phase is. Because you have to first think about what the heck is going on. So, right, we're at a really weird point. We're at super high temperature and super high pressure. And so basically what happens, trying to zoom in on this picture here. So at our subcritical level, right, we can have this phase boundary. But then as we heat up to our supercritical limit, right now there's no phase boundary. And so it's just this really weird, you know, again, highly pressurized supercritical fluid. And so that's, again, what it is, very extreme, so we don't need to focus on that. But just, again, note that it's way out there, right? Your point at this end is your critical point. Let's see, so we went over, again, all, right, your curves. I think that's pretty much the relevant data. And then just pointing out, right, 760 torr, so that's normal boiling point, right? So solid to liquid, sorry, would be normal melting. And then where's our normal boiling, right? So the normal boiling, liquid to gas, would be at this temperature. And they did mark it for us. Sorry, you had a question?
With triple points, is that more likely to happen with like hydrogen bonds?
Well, it's just wherever it occurs, right? So every substance will have a triple point. It's just where it is. And so then, yeah, the different intermolecular forces will kind of dictate where that triple point is. But yeah, all substances would have this. Yeah. Yeah, because this is just a phase diagram. All right, so then again on an exam, you just want to be able to label those main points, solid, liquid, gas, triple point, critical point, and then write these curves. Your fusion curve going from solid to liquid, your vaporization curve, liquid to gas, and then sublimation. Remember the critical point, it's just this pressure. It's really high, like temperature pressure, but then it's just like this weird supercritical fluid where basically your boundary between gas and liquid disappear and it becomes like one weird new thing. But yeah, it's just like we won't really encounter though, right, supercritical conditions normally. All right, how are we doing on time? Not that great. So blah, blah, blah. Here's just another phase diagram. Again, just kind of showing you solid, liquid, gas. Looking at our 1 ATM, right? So now I don't even know what substance this is, right? But we can see we have 1 ATM. We have our triple point still, right, our fusion to curves. So this would be our melting point down here at not really well defined, but right, -5 or whatever from our scale. And then normal boiling point is 25. So just kind of being able to identify that. All right, we'll probably have to stop here. And then just kind of where we're going, because this basically wraps up our intermolecular forces. And then the rest of chapter 15, we're going to talk about the crystal packing, so right, solids, crystallization, and then just get into a little bit of the material stuff. So we'll finish that up and talk about our valence bond theory. All right, distillation lab today should be fun. I'll hang around on stream for another minute or so. I still lost the cat.
I'm still at formation of plasma. Is there like a graph, phase diagram sort of thing that shows you the quadruple point between the four states?
Well, that's not, like, plasma is, like, again, super weird. Like, it's not really a defined state of matter. Like, it's going to be when lightning hits.
Yeah.
So I don't think anybody has done that. All right, I'm going to stop this stream. Thanks again.